Hello, everyone. So in this free lecture tutorial, what we're going to do is we're actually going to tie all of these gas laws that we've studied together that relate the proportionality between the four variables that define the state of a gas, namely pressure, volume, temperature, and amount of gas in moles. Now, we've studied several of these laws that deal with pairwise relationships. Like, for example, we have Boyle's law, where we're studying the relationship between pressure and volume, again, holding constant temperature and amount of gas. We've talked about Charles's law, where we're now looking at the relationship between volume and temperature, provided that we're holding pressure and the amount of gas constant. We've had a look at Gay-Lussac's law, where we're analyzing the relationship between pressure and temperature. And in this case, we're assuming that we're operating under conditions of constant volume, and the amount of gas is also held constant. And then we just recently have been working with Avogadro's law, where basically we are examining the relationship between the volume of a gas and the number of moles of the gas, where in this instance now we're going to be holding pressure and temperature constant. And we also did briefly look at the combined gas law, where we're able to take a look at the behavior of pressure, volume, and temperature of a gas phase system and see how those changes affect each other. But again, this is under the constraint that we have a constant amount of gas. But what we haven't done is actually come up with a relationship that actually ties all four of the variables together. Basically, the closest we got was the combined gas law, where we were able to look at three of the four variables, but we're going to need to do a little bit better if we're going to be able to actually quantitatively describe gas phase reactions. And so for that reason, we have what we call the ideal gas law. And this, at long last, is the relationship that ties all four of the variables together. And the equation for the ideal gas law is PV is equal to nRT, where again, we know that P is pressure and V is volume and N is the number of moles of the gas, and T is the temperature in Kelvin. Okay. What we haven't seen before, though, is this value R. Okay, that value R is what we call the ideal gas constant. And basically, it's just a constant of proportionality that allows us to tie in the four variables together. This value is actually consistent throughout. Basically, it is 0.0821, and the units for the ideal gas constant get a little bit dicey, so you're going to have to be a little bit patient in learning them. But basically, the units for the ideal gas constant are a ratio. It is liters times atmospheres, and then divided by moles times Kelvin. So again, the units of the ideal gas constant are liter atmospheres per mole Kelvin. This ideal gas law, though, is not foolproof. Basically, there are a couple of constraints or a couple of things that we have to keep in mind. Basically, the ideal gas law operates under the assumption that gases follow the kinetic molecular theory that we learned at the start of the chapter. I'm not going to go into that in extreme detail, since again we did learn this at the beginning of the chapter, and so we've been sort of tying it into our work throughout chapter 11. But for the purposes of the ideal gas law, what that means is we're going to assume that the gas particle volume or the gas particle size is negligible compared to the volume of the gas container. What that means is basically we're going to pretend that these gas particles are so microscopic that their size doesn't really matter. Basically, you're not going to essentially impact the collision behavior between the particles. We're going to pretend these gas particles are infinitely small. And basically the other assumption is that there are no interparticle attractions between gas particles. And what this means is basically when these gas particles collide with each other in the course of chemical reactions, they're not going to stick to each other like two pieces of gum. They're literally going to bounce perfectly off each other like balls on a pool table. So basically perfect collisions where we don't lose any energy at all. And so that's the framework under which we can then use the ideal gas law. Okay, so let's go ahead and actually see the ideal gas law in action and how I would solve a problem using this particular law. So here we have a problem. It says they have calcium carbonate. They give us a little background information. They tell us that it's the main component in limestone. It decomposes when you heat it to calcium oxide and carbon dioxide. So there's our gas. We're told that we have a sample of calcium carbonate that's decomposed. We're going to collect the carbon dioxide in a 250 milliliter flask. And after the decomposition is complete, the gas has a pressure of 1.3 atmospheres. And the temperature of the gas at that moment is 31 degrees Celsius. So they're asking us how many moles of the carbon dioxide were generated. So again, these gas law problems can get a little complicated just because there are multiple variables floating around. And so I think it's always a good idea to start these problems by creating a data table. As I've been sort of reviewing your work online over the past few days, basically I see that sometimes you guys sort of jump right into the law itself, and so sometimes you sort of get lost because you're not sure what variables you do have and what you're trying to find. And so taking a minute to just sort of put a table together and sketch it all out for yourself is useful. So again, here we have a volume of 250 milliliters, okay, and we have a gas pressure of 1.3 atmospheres. And we have a temperature that's 31 degrees Celsius. They're asking us to try to find the number of moles. Okay, so again, the relationship we're trying to use is PV is equal to nRT. I favor the approach where you solve for the missing variable with the letters in place. So then all you have to do is plug in and just do the arithmetic instead of trying to do algebra with the numbers present. So here I'm trying to solve for the n, right? I want the n by itself. So what I would have to do then is I would have to divide both sides of my ideal gas law by RT so that I isolate the n. So if I do that, that means my new equation that's going to give me my number of moles is PV over RT. But before I plug in, again, recall that this ideal gas constant has units of liter atmospheres per mole Kelvin. So you should check to make sure that the variables have the correct units to make sure that everything cancels out in the ideal gas constant. We're okay with the pressure. Those units match. Basically, we're not okay with the temperature because I need it to be in Kelvin, but currently it's in Celsius. So if you recall, the way that I convert to Kelvin from Celsius is I add 273 to it. If I do that, so again, 273 plus 31, that gives me a Kelvin temperature of 304 Kelvin. In addition, I'm not okay with the volume because the volume's in milliliters and I need it to be in liters. And so that means I'm going to have to do a metric conversion. So again, 250 milliliters. There are 1,000 milliliters in 1 liter. And if I do that division, I should get 0.250 liters. So that's the value that I want to plug into my ideal gas constant, or my ideal gas law, so that all the units in the ideal gas constant cancel out. And so now we're ready to go ahead and plug into the ideal gas law. So the pressure is 1.3 atmospheres. The volume is 0.250 liters. The ideal gas constant, that's 0.0821 liter atmospheres per mole Kelvin. And then our temperature is 304 Kelvin. Before I do the math, I'm just going to make sure that my units cancel. So liters cancel liters, atmospheres cancel atmospheres, Kelvin cancels Kelvin. Notice that all I have left over are my moles. And so that means that when I do this math, I'll get an answer in units of moles, which is what I'm looking for. So I'm going to multiply 1.3 times 0.25. And I'm going to divide by 0.0821 and then divide by 304, since again both the 0.0821 and the 304 are in the denominator. And that gives me an answer of 0.01302 moles, but again, we still have to keep in mind significant figures. And if you notice, the temperature, the pressure, and the volume are all given to two significant figures. So that means I would want to stop reporting the number here, because basically the zeros are not significant. The 1 and the 3 would be significant digits, so I want to stop there. There's a 0 next to that 3, so that means that the 3 stays. And my final answer is 0.013 moles of carbon dioxide. Okay, so go ahead and answer the questions attached to the pre-lecture tutorial assignment on mastering chemistry. If you have any questions related to the ideal gas law or need any help, again, feel free to reach out via email. Okay, hope everyone's staying safe. Take care.